Today's lecture focus on numericals of energy and power signal. Let us look at the first problem. It says find energy of the following signal. So problem clearly says that you need to find energy. The given signal is an energy signal and you are expected to calculate energy of the following signal. Okay. What is the problem? Xn is 1 by 2 raised to n for n less than infinity, n less than 0, and 3 raised to n for n greater than equal to 0. Okay, try to understand the limits. So this is the xn equation for negative values of n, and this is the xn equation for positive values of n. So let us start to find the energy of the given problem. So energy equation is n is equal to minus infinity to plus infinity mod of xn square. Okay, so what you need to do is, as per the input, we need to modify the limits. So we understand that xn takes different values for different ranges of n. So for negative values of n, xn is defined differently, and for positive values of n, xn is defined differently. So that's why we need to break up the summation limit. So we clearly understand that to solve this particular problem, I need to split the summation. Okay, so I'll split the summation from minus infinity to minus 1. Okay, and second summation split will be from 0 to infinity. Carefully observe how the summations are split. The summation is split from minus infinity to minus 1. Okay, so I'm covering all negative values of n here, minus infinity to minus 1, and here the limit goes from 0 to infinity. Here we are covering all the positive values of n, because as per the given problem, I have two different representations of xn for negative value and for positive value. So accordingly, I need to split the summation for negative values and for positive values. Right, now we will substitute xn according to the limit range. So here the limits represent negative values of n. So xn for negative values of n is 1 by 2 raised to n. So we'll replace xn by 1 by 2 raised to n. Whereas for positive values of n, xn is represented as 3 raised to n. So we'll replace it xn by 3 raised to n square. So here I get 1 by 2 raised to n square. Here we get 3 raised to n square. So we need to solve these two summations to get the energy equation. So let us first of all simplify the summation minus infinity to minus 1, 1 by 2 raised to, it becomes 1 by 2 raised to 2n. And here it becomes 3 raised to 2n. Right. Now to simplify this systematically, let me say that the first summation is represented as A and the second summation is represented as B. Okay. So let us solve these two summations separately and systematically. Let us look at the A summation. So A summation is this part of the summation, minus infinity to minus 1, 1 by 2 raised to 2n. Okay. To simplify this, we will first, the very first step, what we would do here is, we will change the sign of n throughout. To simplify this, we will change the sign of n throughout. So wherever there is n in this equation, we will change the sign of n. So you could see here in the limits are minus infinity to minus 1, which changes from infinity to 1. And here I have n, right? So I need to change the sign of it. It becomes minus 2n. So what you observe, we have changed the sign of n throughout. Wherever there is n in the equation, we have changed its sign. And hence, the limits which were negative are now positive, and the power of n which was positive here is now negative. So why did we do this? So that we could apply the summation identities. Correct? So here the very next step what we did is we have changed the order of the summation. Here the summation was infinity to 1. We have changed its order from 1 to infinity. Nothing changes when you change the order. the result doesn't change, the meaning doesn't change, the meaning remains the same. So instead of infinity to 1, we have written 1 to infinity. And the rest part of the equation is maintained the same. In the next step, this minus 2 raised to n is compensated by taking the reciprocal of 1 by 2. So instead of 1 by 2, I made it 2, which changes the sign to positive. So 2 raised to 2n. So 2 raised to 2 can be further expressed as 4. So what remains is 4 raised to n. So now I have an equation, right, which is going from 1 to infinity. The limit of the summation goes from 1 to infinity, 4 raised to n. Now let us see how to simplify this using identity. So we know the summation identity is 0 to infinity a raised to n is 1 upon 1 minus a. This is a summation identity, which says that the summation limit should be 0 to infinity and the given problem should be in the form of a raised to n. Then you can apply the identity and express it as 1 upon 1 minus a. Correct. So is it in the form? Is this summation compatible to the form of what we need? No. The very first mismatch is the limits. Here the limit go from 0 to infinity in the identity, whereas in the problem it goes from 1 to infinity. So there is a mismatch in the limits. Rest of the term is fine. A raised to n is 4 raised to n. It means that a value is 4. But the summation limits mismatch. So in order to apply this summation identity to the given problem, we need to modify the limits in the problem. So we need to modify the limits, changing it from 0 to infinity. We need to modify the limits to make it compatible to the identity. So we change the problem limits from 0 to infinity. The moment we made it from 0 to infinity, what is the additional value we have included in the summation which was not present earlier? In the earlier problem, in the earlier original problem, you could say the limits are 1 to infinity. You have changed it to 0 to infinity. It means that you have additionally included a value of n is equal to 0 in the summation, which is not there earlier. Limit starts from 1 to infinity. To make it 0 to infinity, we have forcefully introduced n is equal to 0 value in the summation. So this n is equal to 0 value which we have forcefully introduced in the summation should be compensated. And how is it compensated? It is compensated by subtracting n is equal to 0 value from this summation. So we subtracted n is equal to 0 value from this summation. So when I put n is equal to 0, the function 4 raised to n becomes 4 raised to 0. It means that we have compensated n is equal to 0 value which we have forcefully introduced in this summation by subtracting it from the summation. So we subtracted n is equal to 0 value from this summation and we have written it as 4 raised to 0. It means that this summation indirectly is now going from 1 to infinity because we have separately compensated 4 raised to 0. Now we can apply the identity of summation identity to this particular summation. So here these are now exactly compatible. So using the summation identity, this equation modifies to 1 upon 1 minus a, where a is nothing but 4. So 1 upon 1 minus 4. 4 raised to 0 is nothing but 1. So simplifying this particular summation, we get the value of the a part of the summation to be minus 4 by 3. So the a part of the summation is having a value of minus 4 by 3. Similarly, now we need to proceed and solve the b part of the summation. So the b part of the summation, right, is this part of the summation. We have now completed the a part. Let us now calculate the b part of the summation. Right, so b part of the summation is this summation, n is equal to 0 to infinity 3 raised to 2n. So 3 raised to 2 can be expressed as 9 raised to n. right? Can I apply identity to this summation? The summation identity, as we just discussed, is n is equal to 0 to infinity a raised to n is 1 upon 1 minus a, right? So is it compatible? Is it perfectly matching with the identity? Yes. So I can apply this identity and calculate the b part of the equation by replacing this part as 1 upon 1 minus a. So what do we get? My a here is nothing but 9. So 1 upon 1 minus 9. So when I solve it, the b part of the equation is minus 1 by 8. The b part of the equation is minus 1 by 8. So now we need to add the a part of the summation with b part of the summation to get the total energy of the given signal. So in the last step now, we have added the a part answer and the b part answer. A part was minus 4 by 3. The B part answer was minus 1 by 8. So the overall energy when this equation is simplified is minus 35 by 24. So the given signal has energy value of minus 35 by 24. This is the problem all about. Now let us try to discuss another problem. Again, the problem here specifies us to calculate energy of the signal xt. So it's a CT signal now. So we need to find or determine the energy of the signal. So the problem clearly specifies only to find the energy of the signal. How is xt defined? So xt is defined for three different values for three different time periods. So xt is defined over three different time periods, right? So xt has a value 5 minus t for a time period between 4 to 5. Xt has a value 1 for the time period between minus 4 to 4, and xt has a value t plus 5 in the range from minus 5 to minus 4. So xt takes different values for different time periods. So this is the given information with which we need to find the energy of the signal. So let us start with the energy equation. So we know energy is defined as minus infinity to plus infinity mod of xt square dt. Be careful when you write the energy equation whether you are applying it for a CT signal or a DT signal. So the given signal is a CT signal. So here comes the integration. Minus infinity to plus infinity mod of xt square dt. To simplify this energy equation, look carefully the way the problem is defined. So we know that the problem is defined for three different time periods outside of which xt is 0. So we need to split the integration satisfying the given input. So we need to split the integration from minus 5 to minus 4, then minus 4 to 4, and then 4 to 5. So we are going to split the integration in three different parts. So the first limit is minus 5 to minus 4, second is minus 4 to 4, and third is from 4 to 5. So this is how we have split the integration. Now let us substitute the corresponding value of xt as per the limit of the integration. So from minus 5 to minus 4, in this particular time period, the signal xt takes a value t plus 5. So we replaced xt by t plus 5. The second limit is minus 4 to plus 4. In the region from minus 4 to plus 4, xt takes a value 1. So we replaced xt by 1. And the third limit 4 to 5, in which xt takes a value 5 minus t. So we replace xt by 5 minus t, square of it. So this is how we have formulated the energy equation. Now what remains is the mathematics. We need to solve this. So in the very first step, we have taken the square of this signal. We have taken the square of this signal, right? And then integrated each of the terms separately. So integration of t square is t cubed by 3 Integration of t becomes t square by 2, and integration of 25 is simply t, and we are putting the limits to each of the term. Similarly, integration of dt is nothing but t, limits of which are minus 4 to 4. Similarly, for the last integration, the first term is 25 integrated. So 25 integrated would be only t with the limits 4 to 5. 10t integrated would be t square by 2, and t square integrated would be t cube by 3, and the limits are accordingly put. When you simplify this, put the corresponding upper and lower limits, the energy equation for this particular signal is 8.66. So the energy value of this signal is 8.66. So what is important is carefully splitting the integration and putting the value of the signal xt according to the integration limits. Let's move to the next problem. What is the next problem? The next problem says determine energy and power of the given signal. So there it has been asked to determine energy and power of the given signal. So we need to find both. So let us first focus on energy of the signal. So we know that the given signal is a dt signal. There is a term n which comes here, which indicates that the given signal is a dt signal. So we use energy equation of the dt signal. So n goes from minus infinity to plus infinity mod of xn square. So energy equation, in the next step, we replace xn by the given equation e raised to j pi by 2n plus pi by 8, mod of it is to be taken as a square. Okay. To simplify this equation, we have generalized e raised to j pi by 2n plus pi by 8 as e raised to j theta. So here we are indirectly intended to find mod of e raised to j theta. So what would be a generalized answer of finding mod of e raised to j theta? So we know that e raised to j theta can be expressed as cos theta plus j sin theta. And we are intended to find the mod of this. So we are finding mod of cos of theta plus j sin theta. So mod of a complex number is nothing but root of the square of real part and the imaginary part. So square root of real part square plus imaginary part square would be the magnitude of this mod. So square root of cos square theta plus sin square theta. We know cos square theta plus sin square theta is 1, and hence e raised to j theta, irrespective of what your theta value is, mod of e raised to j theta is always 1. And hence, if I apply to the given problem, then mod of e raised to j pi by 2n plus pi by 8 will be 1. This value will be 1 irrespective of what your theta value is. So if I now put this mod value into the energy equation, I get n is equal to minus infinity to plus infinity 1 square. 1 square is 1. What is the meaning of this particular summation? Here the summation indicates that your summation means it's an addition. You're adding 1 how many times? You're adding 1 from minus infinity to plus infinity times. The equation indicates that you are adding 1 from minus infinity to plus infinity times. So 1 plus 1 plus 1 infinity times is nothing but infinity. So the energy value of the given signal is infinite. We understand here that the energy of the given signal is infinite. The problem says that we need to find the power of the signal also. So let us now proceed to find the power of the signal. So the given signal is dt signal. So the power equation is limit n tends to infinity 1 by 2n plus 1 summation minus n to n mod of xn square. So using this power equation, we will replace xn by e raised to j pi by 2n plus pi by 8 square of it, mod of square of it. So as we just discussed, mod of e raised to j theta is always 1. We just have discussed that mod of e raised to j theta is 1. Right, so when xn is replaced by the given problem, right, we get mod of e raised to j theta. This is in the form of mod of e raised to j theta, which is nothing but 1. So what remains in the power equation is limit n tends to infinity 1 by 2 raised to n summation minus n to n in as summation of 1. So what is the significance of this summation? This is very important to understand. N is equal to minus n to n with the summation value to be is 1. Where you add here the summation is 1. So how would you interpret this part of the equation? What is the meaning of summation? Summation means you're adding. You're adding 1 how many times? You're adding 1 minus n to plus n times. You're adding 1 from minus n to plus n times. So total times you're adding 1 is 2n plus 1. This simplifies to 2n plus 1. So this particular summation, you're adding 1 minus n to n times, and hence this particular summation, so total number of ones when counted turns out to be 2n plus 1. How we could simply do that? Right, this summation can be split as 0 to n. So 0 to n means you are adding 1 n times, and what remains in the remaining part summation? Minus n to minus 1. So minus n to minus 1 indicates you are adding it n times. So 0 to n means you are adding n plus 1 times, and minus n to minus 1 means you are adding it n times. So total it turns out to be 2n plus 1. Right? You are adding 1 how many times? 2n plus 1 time. So this summation results into 2n plus 1. Right, so these two terms gets cancelled. What remains is simply 1. So energy was infinite, power is finite, and we know that when power is finite, energy is infinite, the given signal is a power signal. So we conclude here that the given signal is power signal. Okay, let's move on to the next. Next problem is determine whether the following signal are energy signal or power signal. And what is the question? The question is xt is equal to RT. Now what is RT? So RT, as we know, is a standard signal which is the ramp signal. RT is a ramp signal, right? So RT takes a value of 0 when t is 0, RT takes a value of 1 when t is 1, RT takes a value of 2 when t is 2, RT takes a value of 3 when t is 3, and so on. And therefore ramp signal is a linearly increasing signal. It goes up to infinity as t tends to infinity. So this is the ramp signal, and we have been asked to find its energy and power. So since this is a CT signal, we write the energy equation as minus infinity to plus infinity mod of xt square dt. We'll replace xt by the given ramp signal. So instead of xt, we will represent xt as rt. So the equation is mod of rt square dt. Now what is the equation of a ramp signal? So as we know, as t is 0, rt takes 0. When t is 1, rt is 1. When t is 2, rt is 2. It means that rt is nothing but t. Rt takes the value of t. So Rt basically is represented by the equation t. So we'll replace Rt by t. So the equation modifies to t square dt. Look at the limits. Since Rt, the ramp signal, exists only for the positive values of t, the limits of the integration modifies to 0 to infinity. the limits get modified to 0 to infinity, as Rt, the ramp signal, is existing only from the positive values of t. Accordingly, the limits were modified. Rt was replaced by t, right? And now we need to take integration of this. So integration of t square is nothing but t cube by 3. The integration of t square is t cube by 3 with the limits 0 to infinity. So when you put the upper limit, you get infinity, and when you put the lower limit, you get 0. So infinity minus 0 is nothing but infinity. So the given energy value of the ramp signal is infinity. So energy value of the ramp signal is infinity. Let's proceed further and find the power of the signal. So power equation is limit t tends to infinity 1 by 2t minus t to t mod of xt square dt. So we'll replace xt by the ramp signal. We know our ramp signal is represented as t. So t square dt. And limits minus t to t becomes 0 to t. So what are the two modifications we did in the input signal? Firstly, we modified the limit because the ramp signal exists only for the positive side of the signal. So limit get modified to 0 to t. And the second modification which we did was we replaced xt by the equation of the ramp signal, which is t. So it becomes t square dt. So you need to solve this integration first. So this integration is t square. Integration of t square becomes t cube by 3. Integration of t square is t cube by 3. And we need to put the limits 0 to t. So when we put the upper limit, you get t cube minus 0 by 3. So which results into t cube by 3. So when I put the limit, upper limit is t cube minus the lower limit 0. So t cube by 3 is what we get. So this t and one of these t gets cancelled, and we get the limit to be we get the equation to be t square by 6 with the limit t tending to infinity. The moment we put t tending to infinity in the equation, infinity by 6 becomes infinity. So here is a very interesting revelation we have got. We observe that the energy equation is also infinite, the power equation is also infinite, right? Here we obtain power to be infinite, and we have also obtained energy to be infinite here. The energy is infinite, the power is infinite. So what is the conclusion? What is the conclusion? So we conclude here that the given signal is neither energy nor power signal. The given signal is neither energy nor power signal. Why? Because both are infinite. Both energy as well as the power signal of the given signal is infinite, and hence the given signal is neither energy nor power signal.